morning. Welcome to Information Security. We will today cover the topics from two lectures, not just the rest of the memory safety lecture, but also the rest of the entire side channel lecture. So far, there are only about 50 people in the stream, but I hope we will have a few more in a second. And before we start with the content for today, we can also first run through a short quiz. And this gives the others time to arrive. So let me just move to the right slide here. So you should be able to see the Menti, but for some reason you can't see it. Let me check why you can't see it. I just have to quickly figure out where my Menti window is gone. Here it is. And there we have the Menti window. No, it still doesn't work. Interesting. So it should be here and should already show something. So the question is where it is. There's no break now. Let me just find my Menti window, or let me open maybe a second one because I can't manage to open this one right now. Okay. Yes, this one works. Okay. So here we have the Menti window, and you can see the number up there. Let me move this a bit over here. And now you should be able to see it. If it works for you, please let me know, and then we will be able to start in a second. So you can just log in with this Menti code up here. And as soon as you've done that, I see that some of you already have. And then we can start with the Menti in a second. So let's see how many people we have in the stream so far. We can already see a lot of people are logging in, 22, but there should be a lot more, right? There should be 10 times the amount registered for this lecture. More than 10 times the amount. Mhm. Okay, but I would say let's just start with the quiz. And the first question is, this is then another good thing. Okay, let's try this. Okay, just jump back. Now it seems to work, so let's hope that it keeps it this way. But it works. It works. Okay. So I would say let's start. We now have about 30 people in the quiz, so let's start the quiz. And the first question is, next to a buffer on the stack is global variables, shared memory, or the saved return address. Time is already up, and most of you have correctly answered. It's the saved return address. And that's very problematic because you can overwrite the return address and by that make some other program run into some part of the code that usually shouldn't be executed. The next question. The two types, let me start the question first. And always keep in mind to check the phone because the phone shows the prompt earlier than the stream. The two types of memory safety violation are segfault and invalid free, local and global, spatial and temporal, or severe and non-severe. Oh, this is really unfortunate. The correct answer. Let me just. Can I still enter this here? I can't. The correct answer would have been spatial and temporal, so these are correct. It's not segfault and invalid free. Those are not types of memory safety violations. These are the types of memory safety violation. We distinguish these because spatial, that's basically where do we access, and no matter when this access would happen, this is a wrong location that we access. Temporal would mean that it's the wrong point in time for this activity. For instance, if you have a double free, the free itself is not wrong, but it happens at the wrong point in time because it was already free. Or use after free. If you access a memory location after the free, that's not wrong if you would move it to a different point in time. So the time for temporal matters a lot. Let me go to the next question. And I hope that everything worked here with selecting the correct answer, because sometimes I get that wrong. Let's try. Printf input is dangerous because new line might be missing, or %n can write to memory. There are also more reasons, but I wanted to focus on these, on this one. Very good. Everyone got that right. Then we have, next one. GetS is dangerous because the required buffer length is unknown, or the user might not enter a new line. Yes, very, very good. Let's have some applause here. And currently the cat wants out. So let's continue, and we will continue with some slides. So let me move to the slides. Or before we do that, maybe we should have a look at the leaderboard. So let's see who answered all the questions correct. And in this case, it was Git Profit and also a few others who answered everything correct, as far as I can tell. But the timing here made the difference. So congratulations. Round of applause. Okay, and now, now we still don't have that many viewers in the live stream, I must say. It's still only 60, but I think we will just continue with the slides for today. So we talked about these memory safety vulnerabilities, and one thing that we didn't talk about is what if we cannot prevent all of these attacks, right? Sometimes it's not possible to prevent all these attacks. Sometimes the attacker still can exploit a vulnerability. And I see there are already questions in the Menti. I will go to that in a second, but I also see that the chat is not working. Yes, so the chat is working now. Let me see. The slides are, I think I uploaded the slides. I think they are in the C files repository. If you just change the URL to I think s2_site_channels.pdf, this should be the URL there. So they are uploaded, but I'm not sure whether I put link anywhere. So let's continue maybe with the slides. So let's assume we can't prevent an attacker from exploiting a vulnerability, because vulnerabilities will always exist. So the question is just, what do we do then? And what we can do is we can prevent attacks from doing any damage by constraining them into certain areas. So we want to restrict the attacker after the exploit was already running. Protect our system even if the applications are controlled by an attacker. And this is the concept that you might know already, and that's sandboxing. You just put your entire computer into a sandbox, not a sandbox like this, of course. Yeah. But you can put your computer in a sandbox and then, or your software in a sandbox, and then it would work without being able to access all your more important data. So sandboxing can be used, for instance, using Docker. If we use Docker with our simple password manager that we had last time, the user might still be able to enter nonsense here and might be able to exploit the vulnerability. But what happens if the attacker tries? So if the attacker tries to do that, the attacker might gain access to this Docker container, but the attacker cannot, for instance, write to the file system anymore, because this is not permitted by the Docker container. So the attacker cannot do much anymore. It's possible to exploit the vulnerability, but even if you do, you are still constrained to your Docker file system. When there is time, tell us some fun story about platypus. Oh, I haven't studied biology, so I don't know much about platypuses. but it's certainly a very interesting animal. An attacker cannot do much anymore if you use a sandbox, because, for instance, the file system can be set to read only, or maybe you have a separate file system for the Docker container, and maybe you prevent that files are changed or created. Or even if you can change and create files and the attacker takes over full control of the container is restricted and has only access to the data that is relevant for this container. It doesn't have access to the entire system. So no files of the host computer are visible except the program, and in this case the password list. There's also no network connection in this Docker container, but this depends, of course, on the container, how much damage the attacker can still do. If you run a program and the attacker, if the attacker completely controls the application, then this cannot harm the rest of the system. But maybe there are some worst cases that we still have to think about. For instance, if the attacker finds an exploitable bug, circumvents all the countermeasures and gets a shell in the sandbox and is able to read the password file. How do you prevent the attacker from using this information? The password file, if you think about a password manager, will usually be encrypted. So if it's encrypted, then it's no problem because the key is derived from a PIN and the attacker does not have the PIN because you entered the PIN and it's not stored anywhere. So assuming the crypto is good, and if you used it correctly, then everything should be fine. So if we encrypt the data, do we even then benefit from a sandbox? I mean, the attacker cannot read the password file anyway. And that's of course wrong again, because the attacker could do something without a sandbox. For instance, create and modify files, install a keylogger, and replace the password manager with a manipulated one. Within a sandbox, this might not be possible because the application is very constrained now to exactly the activities that it should be allowed to perform. And that is not replacing binaries. The password manager should never be allowed to replace binaries. It would only do that if an attacker has compromised this. He can also wait until when we type the password. Yes, we can. Yes, a keylogger. So we can install a keylogger and just wait for the password to be entered. But in the case of a sandbox, this might not be possible because the password manager might not be allowed to perform these operations. The attacker will be very constrained in what it can do. Even achieving persistence in the system within the sandbox might be difficult if you have no access to a lot of system calls, for instance, because the sandbox restricts that. So even the best crypto does not help if our system is compromised. So that's basically our conclusion about the crypto lectures that you have heard so far. This is why system security is, I would say, more important than crypto, because crypto cannot help in all the situations. On the other side, of course, we rely on crypto as well to make things secure, but it's only one of the building blocks. So best practice, never assume perfect countermeasures or bug-free code. Encrypt your data in case it leaks, and then minimize privileges. Minimizing privileges is very important today with a lot of software running on a system. So you definitely want to make sure that the principle of privilege minimization is followed. Log everything. This is also an important lesson. I won't go into too much detail here. Log everything. This is important because, and I elaborate more on this in the master's course, secure software development. The problem with security is that you will never achieve 100% security. You will always have the situation that someone can exploit some bug, some misconfiguration, and can then do damage to your system or to your company, etc. So what you definitely want to do is you want to make sure that you know who performed the attack. Ideally, let's assume you have a vulnerable web interface. That is already not so good, but it's technically seen not a problem if this interface is only reachable by users that are fully identified. So let's say a user where you know the exact identity and you can prove that it's this person, for instance, within a company, and you might know which person or you should know which person it is. If you log everything, you will be able to sue the person who did that. And this is the strongest incentive against attackers, that you have legal measures that you can take against an attacker. But in many cases, our systems do not do this, do not follow this principle, or have no way to identify the attacker fully. So in those cases, it's not applicable to just log everything and sue everyone. So it's if you can follow this principle, it's great. But if you can't, then you will have to invest a lot more into security. The compiler, in our case, can help us to harden the application. There are also compile flags like 45 source to make the compiled or to make the source a bit more resilient to attacks. But overall, you can make it harder, you can improve things, you can use automated techniques to improve things, but in the end you will never reach perfect security. The takeaways from these memory safety lectures: we started off with compiler warnings, where we showed that you shouldn't ignore compiler warnings. We talked about countermeasures. Don't disable the countermeasures, they are enabled by default already. Enable countermeasures that are cheap, for instance ASLR, and then there are more expensive countermeasures but stronger countermeasures like CFI that you should also enable depending on your situation. And always consider sandboxing your application. Sandboxing doesn't cost too much, but it can really improve the security of your system. Defending is hard, but not impossible. In the end, you will make it harder to perform an attack. Defenses are important, as said, to raise the cost for an attacker. The security is a cat and mouse game. We've also seen that, where you start off with one attack, then the defender comes up with a better defense, and the blue and red team that we've talked about. And in the end, the best countermeasure is not to have bugs in your code, but this is probably also not plausible. A more realistic view is you will have bugs in your code, but you can try to reduce the number of bugs. And with that, we are at the end of the first part that I didn't cover in the last lecture. And I will get to the first Q&A session for today. YouTube chat is stuck. Yes, I think I fixed that. A question to the last lecture: why is a second free problematic? Because someone in the meantime might have allocated memory again and received exactly this pointer. Now you're freeing a pointer which is unrelated to your pointer. This would be a problem because now you're releasing memory that belongs to someone else. The other part is, if you know how free works internally, you might know this from SLP, you know that free will write to a memory location because it will iterate through a list, and then it will check for the segment that you want to free, and it will set some values there to 0. So this would be a way to set memory content to 0, even if this is not the start of a malloc segment anymore. Does Hexe belong to you or to Maria? She had her too in the live stream. Oh, that's an interesting coincidence. I'm not sure how to answer the question though. A question to the last. Where is it? Where is it? I don't see the question anymore. Okay, it showed me one question twice apparently. So does sandboxing tend to make developers care less and write worse code? I don't think so. It totally depends on the on what you exactly promise. For instance, I've heard about cases where secure enclave technology encouraged developers to care less and write worse code because the users wouldn't be able to see that anyway. Let's say, for instance, ARM trust zone. You wouldn't be able to see what is executed on your phone in the trust zone, and so developers care less and write worse code. But for sandboxes in general, it doesn't immediately mean that you write worse code or care less, because your code might still be, or in many cases will still be readable, because sandboxing is very often used like with Docker containers in combination with open source software. It's more about a system level defense. So you would use that to sandbox applications that you did not necessarily write yourself. So you might even trust this application, but it's better not to trust and just be more careful. Should something like an Apache web server be fully sandboxed? Currently, it's just a different sys user running the application most of the time. Yes, I would definitely sandbox a web server into its own sandbox. Log everything may be bad for privacy. How would we say these concerns should be balanced? Yes, privacy is also very important, but the problem is if someone can perform operations that might be harmful for your system, for the users of your system, then it's also important to figure out who it was. It always depends on what exactly will be logged. You don't have to log every mouse click, but logging every action that could be harmful, that is probably a better idea. Not necessarily all the user input. For instance, let's say to a password manager, you definitely don't want to log all the user input, but you might want to log metadata such as who made the request and was there a deviation in the control flow, for instance, by logging points in the code that you've passed, and basically printing out this as a sort of checksum whether the code execution went through normally. Of course, this would be very specific to this example and maybe also not generic enough, but you can definitely log information in a way that it's not too bad for privacy. So with that, we are through with the first Q&A. So I will go to the next slide again. This one. And we will continue. And let me just check. There were also questions in the YouTube chat. So what do we have here in the YouTube chat? What do you mean with sandbox? Like KVM, VMware, Docker, or some sort of what, for example, sandbox does? So a sandbox will restrict the system calls that you can perform. So I would speak of something like Docker. It could also be something like a Shroot container or a yeah, what other sandboxes do we have? Maybe a jail, a fire jail, or something like that. There are various types of sandboxes, and the basic principle is that they restrict system calls or replace system call behavior with other operations. So for instance, instead of performing a file system call to the host file system, they would change all the passes that you can pass to the system call, so that you end up in a subfolder and you cannot reach the rest of the system. So yeah, this is how sandboxes work. Okay, let's continue with the next slide. Information security, system security 2. This is the topic for today. You can also see that it has the right date. And we talk about side channels and microarchitectural attacks. Side channels are very interesting because they exist everywhere. They exist in the real world just the same as they exist in computers. Side channel attacks, we talk about software that you write and is generally secure in a sense of memory safety. And very often we assume that this software is free of bugs. It does not contain any bugs. But still, information might leak because of the underlying implementation. This can be hardware, but it can also be the underlying software implementation if you have, for instance, the operating system leaking the information. So what we do is we exploit unintentional information leakage by side effects. This definition is not unproblematic though, because we have many things in here that are not very clear. What is a side effect? What is a side effect? Does it have to be a side effect? Unintentional, how should we know whether it's unintentional? If I find in my product there is a side channel and then I write in the documentation, oh, there's a side channel, but I don't care. Is it then still a side channel because it's not unintentional anymore, because I do intend to have this there? So this definition is maybe a bit tricky. So my definition of side channels is usually a bit more direct, and I say side channel is obtaining metadata and deriving the data from it. So you have these two steps: obtaining metadata, this is the channel, the side channel, and the derivation step from the metadata to the data. So you infer from the metadata what data was processed. So this is what I would say is a better definition of a side channel, because this also works better for many of the attacks that we will talk about today. There are different side channels that you can use. You can use side channels based on power consumption. You've seen the platypus attack earlier this week. Execution time, we use this very often to perform remote attacks over the network. Or CPU caches, you can check which parts are in the cache or not, often combined with the execution time though. Side channels in software are really great because you can exploit them from software. They can be used for attacks, and very often we use a timing difference there to exploit something. I have a very simple code snippet here that we will go through. Let's check what it does. It is a check pin function. It takes some input. The correct input would be 1, 2, 3, 4. So this is the secret pin. And then it runs through a loop from 0 to 4, or to 3 actually, and it will check whether the input is still correct. So it will perform a string compare. Now, if a digit differs, then you can stop, you can return an error code, and then the pin was not correct. Otherwise, it was correct. Okay, so let's measure the execution time of this. So let's provide a pin and let's measure how long it takes to get a response. 0, 0, 0, 0. All zeros is this time. 1 and then 3 zeros. Oh, that's a lot higher. Let's provide 2 and then all zeros, 3 and all zeros. Okay. I think I see a pattern here, because the digit in this example is correct, the next digit is checked, so it takes more execution time. So let's try this. This takes at most 10 tries to get a single digit. Let's try the next digit, 1, 0, 1, 2, 3 again. And you can see here the time is very high for 1, 2, 0, 0, because it again checks the next digit. And then you repeat this for every digit, and then you have the entire pin. The longest execution time always reveals the correct digit in this example. This is very nice, maximum 10 measurements per digit, so you only need 40 tries to figure out the entire pin. If you would run this as brute force, you would need 10,000 tries if you wouldn't use the side channel, because you have numbers from 0 to 9,999. So what you get here with a simple side channel, with this very small example, already a factor of 250 of improvement. With higher numbers, this factor will increase significantly. And in many cases, an attack on cryptographic algorithms is not possible mathematically with brute force, but it is possible with a side channel if the implementation is susceptible to side channel attacks. Many functions can be implemented with constant time. For instance, in this case, we could just write this in a bit different way. So we will just we will OR to this variable saying whether correct minus input is 0. So in this case, if the input is correct, you would get a 0 in the end, and then you will return whether it was 0 in the end. But sometimes there's still a side channel in the hardware, and then you have a problem, of course. Let's talk about the hardware bit. There's architecture and microarchitecture, two terms that we want to define. Microarchitecture, or let's start maybe with architecture. Architecture, we talk about the instruction set architecture. That's an abstract model of a computer. For instance, the x86 instruction set, you might know that. The instruction set architecture defines which operations you can perform on a computer. It defines which registers are there. But this is all an abstract model of a computer. The actual implementation will differ. So this is just an interface between hardware and software. But the microarchitecture is the actual implementation, and this will differ a lot. If you look at these different processors, for instance, they will all have different implementations of the same architecture. Different microarchitecture, same architecture. Modern CPUs can contain multiple microarchitectural elements. So these are elements that don't exist on the architectural level, but they do exist on the microarchitectural level to implement the functionality of the computer. For instance, caches and buffers. Many of the properties of caches and buffers are not part of the instruction set architecture. Predictors, many of these are not part of the instruction set architecture. So they are transparent for the programmer. The programmer does not see them. And you can use these to optimize the program execution. For instance, by writing code that the predictor can predict very well. For instance, by writing code that follows the principle of locality, and therefore caches give you a lot of performance boost. At the same time, because of the way they work, they introduce timing differences because they make some of the cases faster. Let's take a look at a concrete example. I see a question mark here. I think I might be able to resolve that with the next example, and that is caches. We have a simple example here with printf. We just access a variable here. This is a variable. We have our processor with the cache in the middle, and we have our DRAM here on this side. And if we want to access a variable, this will be stored in memory, so it will be somewhere here in this DRAM. Let's try to access this. The first time we access it, it's not in the cache. The cache is empty, so we have to load it from the DRAM. So we send a request to the DRAM looks up where it is, the DRAM sends a response, and then the DRAM stores it, or the CPU actually stores it in the cache. the second time we access the same variable, it's a cache hit. So we can skip this request response part entirely, and it will be much, much faster. So now there's no DRAM access, a lot faster. In the first case, it was a DRAM access, so it was very slow. And I'm not a good mathematician, but or statistician. Is it called like that? So I don't know a lot about mathematics or statistics, and apparently also not about words, language. But one thing that I know is I know how to plot a histogram, and I know how to look at these numbers. So here we have the access time in CPU cycles, and you can see we try to provoke a cache hit. Doesn't necessarily mean that we got a cache hit. Let me just move this bit down here. Okay. Now it should be able to fit below this. So you can see the access time here, and we are here, the lowest cache hits that we try to provoke are around 60, 70 CPU cycles in this example. And then you can see that it goes higher and higher up. And sometimes when we try to provoke a cache hit, we even end up here with very, very high access times. And probably we just didn't succeed in our attempt to provoke a cache hit. But if you look at the number of accesses, this is a log scale. So that means that virtually all the accesses are here. This is completely negligible. This will be less than 1%, even less than 0.1% of the accesses, where provoking a cache hit does not lead to a cache hit. Now let's take a look at cache misses. So we go for cache misses now, and cache misses only start up here. So this is very, very nice, because now, even without any clue about mathematics or statistics, I can just put a threshold here, right below the cache misses, and say that anything below the threshold is a cache hit. Anything above the threshold will be considered as a cache miss. This is really nice. I don't need to know a lot of mathematics for that. So we can distinguish cache hits and cache misses just by saying, is it greater or smaller than 200 CPU cycles on this particular machine? How does this work? How does a cache hierarchy work? Let's maybe take a look at the cache hierarchy here. So we can see that you have multiple cores in a modern system, and then you have the L1 cache, the L2 cache, you have some ring bus that connects these slices that you have below in the last level cache. I will just change the colors a bit because you can barely see my hand, it seems. If I point somewhere, it's better now. Okay, and what you need to know here is that the level 1 and level 2 caches, they are private. That means that only this core 3 can access the caches L1 and L2 that belong to this core. The others cannot directly access these caches. They would have to go through this ring bus and send the request over and ask, can I get this data, please? The last level cache, on the other hand, is divided into these slices, one slice per core, but they are still shared across cores. Any core can access any slice from the last level cache. And also another property that we will exploit is that these last level caches are inclusive. That means any data that you load from memory into a cache, into L1 cache, into L2 cache, also must reside in the last level cache. Any data in L1 or L2 has to be in here. So if data is not in here, it also cannot be in here or here. So how does this last level cache work? Let's take a closer look at this last level cache, and we have a cache illustration here. It has 2048 sets. The cache line is 64 bytes, so you have 6 bits for an offset. And this memory address here is the physical address. The location in the cache depends on the physical address of the data. The cache index determines the cache set. So we determine basically in which line of this cache we will go. The cache set index. And then within this set, all the different locations, the ways, they are called cache ways, they are equivalent. So the data could be in any of these ways, and we use a tag to determine which of these ways contains the right data. To determine in which cache way you want to store something, you use a cache replacement policy that is pretty much the same as in operating system, the page replacement algorithm, just in hardware this time and for a much smaller scale. With that, we will build our first attack. So we now know how this last level cache works. It's accessible by any process in the system. And any process can just try to access data, try to get data out there. And this is also our first attack: flush and reload. Flushing means kicking something out of the cache, and that's an operation that any process can use on its own data. Reload is also something that you can use on your own data, just accessing the data. And in this example, we will focus on shared memory. So shared memory means that it is the data of the attacker. Even if it's just read-only, that doesn't matter for the cache. So let's assume the data might already be cached in the beginning. If it's cached for one of them, it's cached for both of them. Then in the next step, we flush the data from the cache. The attacker brings the cache into a state that the attacker understands. So initially we don't know whether it's in the cache or not, so there's no information that we can gain from that. But by bringing the cache into a state where the attacker says, oh, now I know the data is not in the cache, the attacker can wait for the victim and wait whether the victim accesses the data, loads it into the cache. And the attacker can then re-access it and say, well, if it's fast now, then the victim accessed it. If it's slow now, then the victim clearly did not access this memory location. And with that, without any permissions, we can infer whether a victim accessed a certain memory location or not, and infer what the victim did. So let's work with flush and reload a bit. So we have some struct shared data, and we will run this line of code, return shared data AT4. And if this is the secret, that goes into this statement, then this is really bad, because flush and reload can just iterate over this array and determine, oh, here was the low spike, here was the timing low, so they must have returned AT4. So by seeing the faster access time, we can infer that the victim used this offset in this array. Let's perform a flush and reload attack on keystrokes, for instance. For instance, here in this example, the user types in a password. Is it a password? Let me check. We don't see whether it's a password, but I assume it's a password. And now we can just monitor whenever the user presses a key. Why is that relevant? You might know these swipe keyboards. You can train the same neural networks that are used behind some of those to just put in the timing differences, and they would still be able to infer what you typed. So just the inter-keystroke timings, the movement from one key to another, will reveal what you typed. And this is not so counterintuitive. If you think about it, if you are typing, there will be a distinct pair of timing by moving from one key to another. Moving from Q to W will maybe take less time than moving from Q to something like T with your left hand. Or if you swap from a left hand key to a right hand key, this will be very, very fast. So this reveals very distinct patterns for letter combinations, for letter pairs. Flush and reload does not reveal the actual key, but the timing difference can be used to infer what you typed. Other things that you can observe are, for instance, double fetches. Let's try that. So we have a path here and the payload here. And maybe we want to change the path here. We have a double fetch bug and we want to exploit this. So we perform a string copy operation of this into the string. And then we would open the string. And then we switch to the kernel and so on. And the kernel would also allocate memory for this string and then work with this data. Now what we can do in a second thread is to set this string at offset 10 to x, which overrides the null byte and makes the string longer than it was before. Afterwards, the victim, the kernel in this case, would perform a string copy from string to local, and this would now be very bad because we changed this string in the meantime. So this was working with a short path, a short length, short string length. This allocated a short string length, and now we are overwriting some part of the heap. We have memory corruption here. So let's take a look at how this works with flush and reload. We measure how long the access time takes. Plot this on the x-axis here, and then you can see here's a memory access. This was the first memory access. You can see that first memory access here by the string length. So we now know that it started with string length, and we should quickly change the null byte into an x. So we do that, we change the value, we see the second access here. So how do we do that? First access, second access, we detect the double fetches, and now we, after the first access, toggle the value, change the value, and the second access works with the modified value. This is only 2 applications of flush and reload. There are way more. You can use flush and reload. It has been used a lot to break crypto. It has been used in transient execution attacks that we will talk about later today. And then we have also the prime and probe technique that I will explain now, which is an alternative to flush and reload. Because one disadvantage of flush and reload is that it requires shared memory. Let's assume we don't have shared memory. If you don't have shared memory, you can't use flush and reload. Let me just check what the question in the chat is. How is this measured? Is this possible in user mode? Yes, you can just use a user mode instruction RDTSC for that, which allows you to get a nanosecond precise timestamp, or actually more than nanosecond precise. Very nice if you want to measure timing very precisely. RDTSC is a good choice in user space. So let's talk about prime and probe. Prime and probe allows you to. Why is the string already cached? In the example before, just because I said I don't know, it might have been that it's not cached, but I wanted to illustrate that if it's cached, that it's cached for both. But in general, you don't know whether it's already cached. The important part is that you bring the cache into a state that is known by the attacker, because then the attacker can observe whether the state changed. If the attacker does not know what this state is, then the attacker cannot observe whether the state changed. And we do that by flushing the data and then accessing it later on again. Let's talk about prime and probe as a second technique that does not require shared memory. In this case, we don't access a memory location, but we fill the entire cache or a part of the cache with our own data. Now, if the victim performs an operation, it will replace some of this data. And if the attacker accesses these memory locations again, the timing will be low if the victim did not access anything, or high if the victim accessed something. So I need to force the program to load the string first? No, you don't need to force the program to load anything there. It's not necessary that the cache line is in the cache first. That is not necessary. It was just an example to illustrate that if something is cached for one process, it's cached for both. Let's talk about an example with prime and probe. RSA, for instance, you know RSA already from the crypto lectures, and I don't know RSA that well. I just know that you can implement it with a square and multiply algorithm. And this works pretty much like this. You have your exponent here with ones and zeros. You get a result here. You take the number C and basically either, so this is what we start with. And then for every one, you would multiply the result with itself. So you would square it and additionally multiply C to it if it's a 1. If it's a 0, you would skip this part. So you would only square but not multiply. 0 and then a 1 again. C is again multiplied to this. And yeah, this is how square and multiply works. And let's now think about how to implement this. Well, this would be different functions and they would be at different addresses. So why not just monitor the corresponding cache sets with prime and probe, where we see whether or not this multiply operation was executed. And we did that. And you can see the raw trace here. And maybe a question for the chat, who can already see the key? Who can already see the key? Maybe no one. That's a tricky one. Let me help you a bit by adding something very simple, a moving average. Looks like this now. Can you see the key now? Again, this is a timing trace. So high timing means something else than low timing. Let me add the solution here and you will immediately see it. 1, 1, 0, 1, 1, 1, 0, 0. So you can see every spike is a 1 and every valley is a 0 or multiple zeros. You can see here by the length of the valley, you can determine how many zeros this is. And it's like, oh no, that's unfair. It's like, that's out of scope. You're not allowed to do this. Yeah, of course, we can do this. So let's talk about a different example. This is side channels, but there's also another thing that we need to know when talking about side channels, and that's a covert channel. A covert channel is basically a special form of a side channel application. And in this case, in the examples that we have seen so far, an attacker attacked a victim and the attacker wanted to get information, but the victim did not want to share this information. In a covert channel, you change this. The two programs want to communicate, but they are not allowed to do so, so they have to use a side channel to communicate. For instance, because there is no communication channel, maybe because we are running in a sandbox and networking is disabled, or maybe because all the channels are monitored and programs are stopped whenever there is a communication attempt. How can you differentiate a 0 from no number? The values look the same. The length of the value will determine how many zeros there are in the previous example. So what can you do if everything is monitored or if there is no communication channel? Just use side channels and stay stealthy. So how does that work? We have our spy here, we have our application over here that has access to our images, and we want to get past this firewall that prevents us from communicating over the network or through some file system layers. And we do that by just transmitting the data through the CPU cache. So let's see how this works. We have a sender and a receiver here, and this is the last level cache again. and we will simply access all these sets, evict all these sets, and this means filling this with data, with other data that the other one won't access. So we evict all of these, and then the sender wants to transmit this information 0, 1, 0, 0, 1, 0, 0, 0. And now the attacker will just access or also evict these cache sets where it wants to transmit a 1. And the receiver then can measure which ones were slow. So sender and receiver here collaborate on transmitting information. The sender, let me go back to the step, the sender brings the cache into a known state, and then the attacker, the receiver brings the cache into a known state, then the sender accesses locations, and then the receiver measures based on the knowledge that it just changed the state, which of the sets were accessed. And then transmitting different data works in the same way, and we can transmit a lot of data with that. So just to give you an impression of how fast these things are, we are talking about transmission capacities of multiple megabytes per second here. Transmitting data through the cache this way, multiple megabytes per second. Yeah, there are also other microarchitectural elements. For instance, the TLB, there's the DRAM, there's the memory bus, execution units, there's branch prediction buffers. All of these have been exploited in side channel attacks and in covert channel attacks. So far, we've only talked about memory accesses. This was only metadata. This was side channels. Metadata, not actual data. But we can still deduce data from that if the memory accesses are secret dependent. In some other cases, side channels also can be part of an attack. Let me just take a look at the time. So we had 9:30. So we, I think if we would have another break about now, that would probably make sense. So before we, maybe we go on for maybe 2-3 more slides, and then we will have a break. There's another question. I don't get it. How can some network applications set cache states? Do you mean, for example, on NIC level? No, you execute code on the processor. By executing code, you access the cache. There's no way to not access the cache. So you will always have cache access patterns. Yeah, let's talk about using side channels as a building block. For instance, in transient execution attacks, this has been done a lot. For conventional memory corruption attacks, we've already seen that. Yeah, but you can also use them as building blocks, for instance, when trying to break KSLR or ASLR. This has been done a lot, or to determine meta information like the length of the password, or to transmit information. But transient execution attacks, they push this completely onto a new level, and we will talk about these now. First, let's talk about Meltdown. Meltdown is a CPU vulnerability. It's a bug in CPUs. It was discovered in 2017 by multiple independent teams, and they all participated in an embargo then, and the attacks were disclosed then on January 9, 2018. Meltdown completely breaks the process isolation. It allows reading the data from other processes. The side channel attack, flush and reload, is the core of Meltdown. It's at the core of Meltdown. It's a building block, but it's not strictly necessary. You could replace this building block by other equivalent building blocks. So how does this work? Meltdown, the basic idea is that the kernel space is isolated from user space because you have these privilege boundaries. You perform system calls, you jump into the kernel space, you operate in the kernel space, then you go back. And you can't just cross this privilege boundary. You have this bit, this user space accessible bit in the page tables, you can't just bypass this bit. If you try, your program will crash. This isolation is a combination of hardware and software because the software will configure this page table level isolation. User applications cannot access anything from the kernel, therefore. The well-defined interface, as said, is system calls, and this is how we can still operate and interact with the kernel. Now, in modern processors, the execution of instructions doesn't work exactly like in the old ones. You might know this from computer organization. Fetch, decode, execute, memory access, write back. Simple pipeline. So you fetch, you decode, you execute, perform a memory access, and you write back the data, for instance, by updating the architectural register file. This is in-order execution. Instructions are executed in order, and the pipeline will stall when stages are not ready. If the data is not cached, we need to wait. But this is not really great because this doesn't have a lot of parallelism, right? We want to have parallelism, and this is how we envision it, right? And then in practice it will look something like this. Let's talk about out of order execution. So let's think about this simple program here. We have some widths and heights, and then we perform some computation, and then we print it. And you have some dependencies in here, but you can also parallelize many of these steps. And for this, we need out of order execution. Out of order execution makes pipelines a lot more complicated. At the same time, it also takes out some of the complexity by not requiring to have one execution unit being able to perform all the different things, but you can have different execution units that are focused on one special purpose. So instructions are still fetched and decoded. That happens in the front end. Then in the back end, they are dispatched and executed and processed by the individual execution units. The instructions are executed out of order, but they still appear to be executed in order to the programmer. So what the processor does is the processor waits until dependencies are ready. For instance, operands are ready, already fetched into the caches. And then later instructions, if you have to wait, might already execute prior to the waiting instruction. But as I said, they will retire in order, so that means that to the programmer it will look like everything is in order, not out of order. Exceptions also can occur. For instance, if you perform an access to kernel memory, your program will crash, and this means a CPU exception or a CPU fault, a page fault maybe. And they are checked during retirement. So before we still execute our instruction, and then at retire, we check, did it work? If it didn't work, then we flush the pipeline and recover the state. So the state, the modified state, does not become architecturally visible, but we should take a look at a very simple example here. Let's take a look at this code. We have a pointer here, pointer dereference, volatile character pointer, null. We take the null pointer and we dereference it. This will crash, right? This will definitely crash. Array 84 times 4096. Okay, then we perform an array access after the null pointer. Why do we have volatile here? Because otherwise the compiler was not happy. It showed this warning, so we had to add volatile so that the compiler really runs this operation. And then the static code analyzer is still not happy. The static code analyzer says, yeah, this is doesn't make any sense. But if we execute this and just use our flush and reload code from before to check which part of the array is cached, we will see that this part was still executed. The unreachable code after the null pointer was actually executed and the exception was only thrown afterwards. Okay. Let's maybe pause here before we go too far into the details. And I will just hide the slides for now, and let's quickly go through some questions in the Menti and in the YouTube chat. I've seen there are quite a few more. Isn't this very dependent on the architecture and type of server running? All the processors today have caches. There are no processors that you would use in a server that doesn't have a cache. So all of these are susceptible to cache attacks. So this out-of-order execution is completely hidden from developers. Yes, it's completely hidden from developers. I cannot reorder that with instructions or stop that with compiler flags. Yes, you cannot do that. This is deeply integrated into the hardware. How can we still check that it was executed when the program crashed? We've just seen with prime and probe, with the covert channel example, we don't need shared memory. But even if we do need shared memory, let's assume this array was a shared memory array. I can check whether or not the data is cached from a second program, which also has access to this shared array. Okay, let's check questions on Menti. Does it work? Yeah. Do I need to infer timing to know what was typed? No, you would infer what was typed from the timing if you would perform a cache timing attack on user input. So it would work the other way around. You don't need to know what the user typed to perform an attack. Isn't it also a danger to print username? Yes, this would be the same as printf with any input. Not so much because of backslashes and other characters, but because of, in the case of printf, it would be format strings. Could you upload the slides before the lecture? I think I uploaded them to C file, so I'm not sure. I think you should be able to access them on the C file repository. I can post a link to the C files during the break. What is your opinion on the fact that we will get more and more ARM CPUs in consumer devices? I think ARM CPUs are already completely dominating the market. If you think about smartphones, who has a phone with a non-ARM CPU? A smartphone with a non-ARM CPU? No one. So it is already completely dominating the market with billions of devices. So there's no change happening here actually. And then I would hide the Q&A again, and we will go for the break and see you after the break.
There's one thing you should know about me. I specialize in a very specific type of security. Microarchitectural security.
You're talking about Meltdown.
Mr. Van Burg has an idea he would like to discuss with you.
Spotting Meltdown?
Not exactly. We turn Meltdown around. You bring the subject into a vault and then they fill it with their secrets.
Then you break it and leak it.
Well, it's not strictly speaking leaking. It's called load value injection. I think we overlooked one square. And this last square, that's LVI.
We mustn't be afraid to add a few more fences, darling.
Okay, welcome back. Welcome back from the break. We continue with now learning how Meltdown actually works. So I think this is a good start after the break. If you're concerned that you're not live, just check on YouTube whether you are live. You can skip ahead then, and then it's easier to ask questions. So let's continue, and we will now learn how Meltdown works. Now that we've seen the trailer about this other attack, LVI, that turns Meltdown around, we also want to learn how Meltdown works. So out of order execution, we just seen that it leaves microarchitectural traces. We have these traces here in the cache, so we want to exploit them now. We can see them in the cache, but there are also other microarchitectural elements. And we give these instructions a name. These instructions are never executed fully. They are executed out of order, but they will never retire. We call them transient because they are only there for some time and then they vanish. So we can observe the effect of the transient executions through the cache. Very nice. So what we do is we load an address. So the computer has to look up this address. And you can imagine this like in a library, right? I want to read a book, and basically the librarian will go and fetch the book. And either I'm allowed to read the book, or maybe I'm not allowed to read the book. Then I'm, of course, a bit sad. We will do pretty much the same. And in this example, let's imagine you're not actually you're not interested in getting the book from the librarian because you know this won't work. But instead you say, can you please give me a book that starts with the first letter from this other book? And then the librarian will go and look up what is written in this other book, check what the first letter is, and give me a book that I'm allowed to get that starts with the same letter. And with that, I've read the first letter from the book that I'm not allowed to borrow. So what we do is we add a layer of indirection. We get the data from the kernel. This is a kernel address, kernel pointer. We cast it to character pointer. We read one character, 1 byte, write it into a local variable, pass this to the array, and then we check whether any part of the array is cached. And it still works. And this is really nice because that means the permission check is not fast enough. Let's think about how we can exploit this. And for this, we need to take a look at the kernel memory and user memory. This is a virtual address space. It starts at 0 and it ends at -1. Right? This is a signed representation. So it goes from 0 to 2 to the 47 -1. And then it goes from -1 on the upper side to -2 to the 47. So this is user space and kernel space. And in the kernel space, there's a direct physical map. And this direct physical map maps the entire physical memory. So any page that you have mapped in user space will also be present in this direct physical map in the kernel. Very nice. So we can use Meltdown to read from any address, including this direct physical map. The index of the cache reveals the data, and the permission check is not fast enough, so we can just read the entire physical memory, because the entire physical memory is mapped in the kernel space. Okay. Yeah, so this was a very interesting experience for us as well. When we discovered that this works, we just dumped arbitrary addresses, random addresses from the kernel, and dumped the data that was written there. And we really got data from other processes. I saw URLs on my terminal printed out that were currently loaded in Firefox. So this clearly was passing all the process boundaries that we had in the system. Yeah, no bugs, just happy little accidents. Yeah. If you know this guy, this is really relaxing in the evening. If you want to fall asleep, very calm voice, very nice to watch in the evening. And it's also amazing how quickly he gets a very beautiful painting done. So let's generalize this. Meltdown is actually a whole category of vulnerabilities. It's not just the kernel user space accessible check. There are also other checks. For instance, the CPU uses virtual address spaces to isolate processes, and the physical memory is organized in page frames. The virtual memory is mapped using page tables. You might still know this from other lectures. For instance, the address translation on x86. If you take a look at this with the 4 layers and the 48-bit virtual address here, and all of these layers set permissions for the page. Page table entry will look something like this. You have the present bit, read write, user space is accessible. This is the one that we exploited here. And of course, this defines the privilege level, and we can bypass the privilege level. But what if we look for other bits? What about the other bits? I mean, user space accessible won't be that special. So let's try other bits. Let's try the present bit. If the present bit is not set, then we get another attack. It's called foreshadow. That's even worse because it allows you to read memory locations, even from virtual machines that are not even present. So you can read the entire host memory, if it's in L1 though. It's the same mechanism as Meltdown, so we call it a Meltdown type attack, just a different bit in the page table entry. How does foreshadow work? We have our access to some memory location. The page table entry now says it's present. And now we translate the guest physical address to the host physical address. We want to do this. In the L1 cache, we have some data with physical addresses associated. And now what we do is we look up, after we translated the guest physical address to the host physical address, we look up the L1 cache with this physical address, the host physical address that we obtained here, and then get the data from this physical page. Now, if the page is not present, this is the case where foreshadow occurs. Now it's not present, and so this translation from guest physical to host physical cannot occur. It cannot be done. So what we do instead then is we use the guest physical address, which sort of can be seen as a host virtual address, and now we look up the L1 cache with this wrong address. And this completely bypasses, of course, all the security mechanisms that virtual machines have in place. The countermeasures that we designed, Kaiser, KPI, KVA, do not help here, but software workarounds do help. For instance, flushing the L1 cache on VM entry, that's very expensive. Disabling hyperthreading, because otherwise you could load data into the L1 cache again. And the workarounds might still not be complete. There are lots of different Meltdown attacks by now. You can see a tree, a systematization tree here with all the different Meltdown variants. And the root cause is always very similar in different cases. So you have an operation that is executed, you have some data here and some data dependency, and the subsequent operation depends on this data here. And accessing this data will lead to an exception. And until here, this is possibly architectural. This is fine. This will execute. These instructions here will retire. But this cannot retire without an exception. So what happens is you run into transient execution here. These operations will be executed, but they will never retire. And then you have the operation that accesses the data, and the data should be thrown away. This is what usually should happen, and no data should then be provided to the data-dependent operation. But Meltdown bypasses this step. It directly forwards the data. And that's great, and you get a fault, and you get a fault. Everyone gets a fault, and then you have tons of different Meltdown variants. Not just page faults, but all types of different faults. One of the more recent Meltdown variants is zombie load, and zombie load leaks data from the fill buffer. It crosses all privilege boundaries, kernel, VM, SGX, everything. And yeah, microcode assists are here a problem, a new type of fault that we exploit. Disadvantage is that we have only very limited control over what data is leaked, so you have to then apply a few more tricks to obtain the data that you want. What is the outlook on Meltdown? Meltdown is not fully solved, but some Meltdown variants are solved. More Meltdown type issues will likely be discovered in newer processors, but also in the processors that we currently have. And the silicon fixes might not be complete in some cases, also very unfortunate. But we will slowly improve the security there. But Meltdown is not the only transient execution attacks. There's a second one that you should know, and that's Spectre. So for Spectre, this is not about faults. It's about control or data flow predictions. So let's talk about Spectre. In Spectre, the CPU tries to predict the future with a branch predictor based on events learned in the past. And then you speculate that you will take one or the other branch. And if the prediction was correct, if the outcome was correctly predicted, then it's very fast. Otherwise, the results are discarded. Like, okay, maybe we need a better example for that. So before the lockdown and long before the lockdown, actually at least a year ago or maybe 1.5 years ago, we used to go for lunch to a pizza place near in Feldgasse, and there they had this really good Diavolo pizza. And every time we went there, we noticed that the Diavolo pizza arrives the first. Of course, because it's a popular place, we have to call there to reserve a table for lunch. So we would call there and say, here's Theo Graz, we want to have a table for 6, please. And they are like, okay, I know what happens. These are the Theo Graz guys again. I know that 5 out of 6 will order Diavolo pizza again. So what they do is they already start and prepare, let's prepare 3 or 4 Diavolo pizza already, because I'm sure they will take Diavolo pizza. And then of course they are ready first. So this is speculative cooking. Of course, if they are wrong, then they have to sort of clean this up somehow. Maybe then they have some pizzas that they don't need. But I think speculative cooking, it's a great idea. Let's take a look at how processors do that. We have a branch here, if index is smaller than 4, and then we look up maybe a font in our database, and we use data index to look up what should be printed here. Otherwise, nothing happens. And you can see here the memory, the data that we provide. So the index, this is the data array that is accessed. And here's the data that we can access, and here's the key that we shouldn't be allowed to access. And the bounds check makes sure that this cannot be accessed. Perfect. But for the other data that can be accessed, we will access this glyph database and will print a character maybe. This is also in shared memory, because why not? This is not secret data. Why wouldn't it be shared? So we start with index 0. and we execute. We don't know which branch will be taken first. If there's no prior execution of this branch, then the branch predictor might not know anything and might speculate the wrong direction. Oh, how unfortunate. So what happens then? The processor has to correct the mistake and will then execute this branch instead. Okay, now this branch is executed. We access this memory offset here. It's a D, and that means we will have to look up the D here. And this is the part that we can observe in the cache. We can observe that D was just accessed because D is now loaded into the cache. With flush and reload, we now realize, oh, it's cached now. What happens with the next one? Now the processor already has a bias. Now the processor already knows the last time we've been here, it went this direction. I will try this again. So the processor speculates this way, and this is great because this is now the speed up. This is a significant speed up. This is great. So we access A here, and this will then load this glyph into the cache. And we continue with that, T and A. And now the processor by now is really convinced that every time we get here, we will go into this branch, so it can always speculate this branch. And then we go for the next index and we access offset 4, where we see the first byte of the key, and we access this offset. And now we know what the key is because it's loaded here, and we can see this with flush and reload again. So now we leaked the first byte of the key, and it continues like that. Maybe we have to retrain at some point with valid inbounds reads, but in general, this is how Spectre works. Spectre root cause, we have a prediction somewhere in our instruction stream, in our stream of operations. We can see that here, operation, then prediction. Then there's a prediction of data flow or control flow, and then some operation that depends on it. This prediction will be incorrect in the case of Spectre, so we are talking about the misspeculation. And so this is transient execution of further instructions, further operations. And at the point this operation retires, this is still fine. When the prediction retires, the prediction was wrong, so we have to flush the pipeline, and this operation will never be executed. Okay, that's a question. So it ignores the if. It doesn't ignore the if, but let's assume, so we can also go back to the example, to a more illustrative example. Let's assume that you are going for a hike, and you go for a route that you've taken in the past, and you don't take a map, and you don't have your phone with you, but you know the path already because you've been there before. And now you're coming to a crossing, and you don't know where to go, whether to go left or right. You don't remember it. What do you do? Just sit there and not do anything? Turning back? Stopping the hiking? You would speculate in one of the two directions and hopefully figure out that, oh, this was the correct one. I remember this location. This was the right direction. And then if you get somewhere where you're like, oh no, this was definitely not the right direction, then you go the other direction. So this is the same that the processor does here. Instead of sitting there and waiting until it really knows, somehow magically, it will speculate one direction, and then as soon as it sees, oh yeah, this was the right direction, it continues. Or as soon as it sees this was the wrong direction, it will flush the pipeline and return at an earlier operation again. Continue at an earlier operation. Does this answer the question? It does not ignore the if, it takes the if, or does not take the if, depending on what the prediction says. So it just takes a guess, an educated guess based on previous behavior. Many predictors are in modern CPUs, not just a branch taken, not taken, but also a branch target buffer, which tells you for an indirect call or jump. Indirect calls or jumps might depend on a memory location or a register. And sometimes you don't have this value ready in the register. And this means that the processor would have to wait until the destination is known. Instead, the processor can also just say, oh, well, I will guess that it jumps to this address here. Of course, this can be a bit dangerous because how would it know which address to jump to? But it will again base this on past decisions. Are all of these operations reversible? All operations are reversible during speculation. During speculation, you can only perform operations that are reversible. So for instance, if you would write to an I/O device, this would not be possible during speculation, and those operations would stop the speculation, and the processor would then continue at this I/O operation at a later point. So they would also stall the pipeline. Other operations from other threads might depend on it, yes, but they are retired. All the instructions are retired in order. So even if they are executed out of order, you have the dependency chains. So the processor knows whether there's a data dependency. So data dependencies will be resolved in order. And also the retirement of the operations will also be in order. So everything there from the programmer's perspective happens in order. Only operations that don't have dependencies will be performed out of order. Or that where all the dependencies are already clear and resolved. Function return addresses are predicted. So if you have a return instruction, the return instruction will have to read the return address from the stack. Now the stack page might take time to retrieve the return address. The stack page might not be, this part of the stack page might not be cached. The stack page might not even be present. So the processor will take a good guess and return to some address where it believes it should return to. Then whether a load matches a previous store. For instance, if you write to a memory location and then read from another memory location. This could be the same memory location, for instance, because you map multiple virtual addresses to the same shared memory. And in those cases, the processor would have to predict that they go to the same physical address. But it doesn't know that because it only knows the virtual address. And translating a virtual address to a physical address takes time. So the processor predicts whether or not the two addresses will match in the end. So a lot of predictors here. Most of them are even shared across processes. So that means that one process can manipulate the predictors of another process. There are many different Spectre variants, and we basically see now the second part of the tree, Spectre type, with the different predictors, and then you can perform attacks cross address space or cross context or within the same context, and then within or cross context also in place or out of place. That means in place, you mistrain with the gadget that you also want to exploit, as we have seen before in the Spectre variant with the bounce check. But out of place would take a second bounce check, which looks very similar but is at a different memory location, and mistrain the other bounce check with this one. And there are some collisions that allow this. Okay, Spectre is not a bug. Spectre is definitely not a bug. It's an optimization. It's very useful actually. So we don't want to get rid of this. We actually want the processor to speculate because it makes things faster. So why would we not speculate? We cannot simply fix it because every part that we fix about Spectre will make our system slower. There are workarounds for critical code parts, of course. For instance, STIBP. Unfortunately, it's cut off here, but it's called STIBP. This was already here. already in the Linux kernel, but then the SDIBP code was removed again because it was making things so much slower that people said we don't want to have it in our system. They heard the performance a lot, so for now the code is removed. And there we have it again. Performance is more important than security to many, off by default. Security off by default, of course, that's a great choice if you are an attacker and want to exploit these vulnerabilities. Very good. Spectre mitigations. Current mitigations against Spectre are either incomplete or cost a lot of performance. We need more research in this direction, both on attacks and defenses. And efficient defenses will only be possible if we know the attacks better. So, sidechannels so far, we can leak metadata, we can covertly transmit data. They can be used as a building block to leak data. But what about modifying data? Sometimes we want to modify data. Can we also do this? Yes, we can. And this is not called a sidechannel attack anymore, but this is called a fault attack. And we will talk about the fault attack as well. So let's talk about DRAM. You might know these DRAM modules from your computer. They are in your computer. And usually you have multiple of these today, typically 2 for dual channel configurations. And then you would have multiple sides of these DRAM modules. So they have chips on both sides, and you would call them ranks usually. Then each of these chips also is subdivided into a lot of banks, multiple banks, for instance, 8 banks on DDR3, 16 banks on DDR4. You have a lot of rows here that depends on the size of the DRAM module, and then a row buffer down here. The rows store the actual data, and these rows you can imagine like this. These are 64,000 cells, one capacitor and transistor each, and this capacitor stores the charge. By now, this would not be capacitors and transistors of this scale, but instead the capacitor would just be a dead end on a nanometer scale, a dead end wire on a nanometer scale, still being able to store a very, very small capacity, but not a lot. How does reading from DRAM work? We want to read data from this row, so the CPU says, please access this row. Row is now activated. That means it's copied into the row buffer. So then the CPU can access it. If the CPU wants to access this green row now, row 2, the row 2 is activated. That means it's copied into the row buffer, and then it's returned to the CPU. This is slow. We call this a row conflict because we had to replace the row in the row buffer. It's a cache again. It's another timing side channel. That's great. So what if the CPU wants to access this row again? Timing side channel, this will be fast because it's already in the row buffer. Perfect. So we have the row buffer is a cache. We have our cache histogram again. This is the first thing that we do when working on a side channel. We check out where are the corner cases, what is the hit and what is the miss. But there's also something else that we want to investigate here. And the effect is, you might know this from your physics classes from school or from university, from some electronics classes, maybe. Capacitors discharge over time. They lose their charge over time, so you have to recharge them from time to time. And there's a refresh interval that is defined for DRAM, and that is that every DRAM cell has to be refreshed once at least within 64 milliseconds. So the memory controller has to make sure that every row, every cell is refreshed at least once every 64 milliseconds. So we activate a row. And this is now the second effect that we have for these capacitors. Because we are on such a small scale, nanometer scale, there are some interferences between these cells. And this effect is called row hammer. Cells leak charge faster if there are proximate accesses in close proximity. So let's assume we go through this example here. We access this row and then this row and then this row again and so on. After some time, some of these cells will have flipped their value. How widespread is this issue? On DDR3, 85% affected. That's an estimate from 2014. 52% affected, estimate from 2015. But I think the 2014 one is probably more correct. It will be closer to 85 than to 52. Then for DDR4, this was also believed to be safe. At first, the vendors claimed, oh, DDR4 will solve the problem, just as they are now claiming that DDR5 will solve the problem. But we saw bit flips on DDR4 already in 2016, and also an estimation from 2016 was 67% affected. I think there is a newer number by now somewhere in the literature, but it's approximately in this range. So single bit flips allow, what do they allow? We flip bits in memory. Let's maybe go back to this slide here. This row in the middle, this will be 8 kilobytes in size. This is 8 kilobytes, 8 kilobytes, 8 kilobytes. The permissions in the page tables for these 8 kilobytes will be different than for these and for these. That means we might even be able to change memory that we don't even have access to. Also keep in mind that this is physical memory. So that means these 8 kilobytes, these 4 kilobyte pages in the most simple case, they might belong to an entirely different process or to the operating system. So we flip bits in pages that do not belong to our process, and we didn't even touch these memory locations. We don't have to touch them. Is ECC memory safe from this? It's more resilient to these bit flips, but really safe? Unfortunately, no. So the percentage of susceptible ECC memory will be lower, substantially lower, but really safe, no. Yeah, single bit flips, what can you do with that? You can modify instructions because you can modify data on pages that don't belong to your process. You can break cryptography by changing bits. Let's assume you have an RSA exponent and you flip a bit in there. That would not be great because there are some requirements for RSA exponents, and I'm sure that these requirements are then not met anymore, right? If you think of the prime numbers, if you flip a bit in there, very likely it's not a prime number anymore that you've used. And then you can break the key. Changing permissions, crashing systems, you can do a lot of different things. This is purely in software. You don't need any permissions for that. So let's assume you have a program with a password check. Check password. This example again. The machine code here is 747. So it looks like this. 0110100, and this is a lot of zeros and 3 ones. What happens if we flip a bit in this byte? Let's take a look at this byte. This is jump equal. If we flip a bit in this one, it becomes the halt instruction. This is not good. This is a privileged instruction. Our computer would, or the program would then get a general protection fault. X or B, okay, this is already interesting. Now we are changing the behavior of the program. Push Q, we are modifying the stack now. This is a prefix, so it would interpret whatever follows it as a different type of instruction. Jump lower, jump overflow, jump below or equal, jump not equal. This is great. Just by flipping one bit, we completely invert the logic. This is great because now we have jump not equal, and that means that only wrong passwords will work. And we demonstrated that this works on sudo, which was great because then everyone could log in with the wrong password, but the user with the correct password could not log in anymore. Very nice. In the future, we will see more attacks that exploit performance optimizations in hardware. New variants of Rowhammer, new variants of Spectre, of Meltdown. For instance, LVI, you've seen the trailer. We are still working on the full 2-hour movie. We are actually not, but you will see new variants coming out frequently. For instance, new meltdown type attacks, and the full transient execution tree. This is not even the most recent version anymore. You can check this out on transient.fail. There's a more complete tree. So this is growing and growing and growing. Transient execution attacks are a novel class of attacks. They are extremely powerful. We are only at the beginning of these attacks. And many optimizations that we introduce, many side channels that we introduce, become now exploitable. At this point, we reach a unique chance, a unique point in time where we can focus on rethinking processor design. We see a lot of time investment currently going into designing new processors that might be more secure by design. Also, other fields have been in similar situations. The car industry, it's really great if your car can go 200 miles per hour. That's like in the 60s, for instance. You had already very fast cars going 200 kilometers per hour, 300 kilometers per hour. But at the same time, they realized in the 50s, 60s that it's actually not so great that if you run into a concrete wall, that you're certainly dead if you run with a car into a concrete wall, even at low speeds, because you would just fly out of the car through the windscreen into the wall. And then they realized that, oh yes, seatbelts might be great. And people were very much offended in the beginning because they said, oh no, that's my freedom. It's my freedom to drive without a seatbelt. And by now it's completely the norm that you use a seatbelt. It's even required by law that you drive with a seatbelt on. And it really, really drove down the fatal accidents with cars. It really reduced the number related to the number of people that are out on the street in cars. The construction industry, also there, we got more and more standardization that defines what requirements must be met when constructing a building. And this is really important. This is something that we don't have in processors. So security incidents like Meltdown Inspector will continue to occur, also Rowhammer, because there is nothing that would require processors to implement certain security principles. The conclusion is that optimizations in hardware often lead to side channels. Unknown and also new side channels are very likely to exist. And in many cases, you don't need any permissions for attacks. On the other side, building countermeasures is very hard. In some cases, for instance, for Spectre, it's really, really difficult because you will lose performance. You can get more information on these attacks. This was just an overview. You can get more information, for instance, in the course Embedded Security. This has been renamed this semester to Side Channel Security, but the content is still the same. The name has been adapted to the content, not the other way around. You can also check out the playlist infosec at TU Graz that I have in my account, and there you can also see a lot more information, find a lot more information on all of these attacks and how they work. With that, we get to the last round of Q&A for today. I think we're good in time, so let's check out the Menti. So I need playlist for break music, please. I can. This was all CC0 music that I downloaded yesterday. I can share the MP3 with you if you like, or share the website with you where I got this music. I will add it to the YouTube description, the website where I got this. Have you bricked hardware while searching for exploits like Meltdown? No, for Meltdown, no. Meltdown wouldn't brick any hardware. Have I ever bricked hardware while searching for attacks? I don't think so. I think in my group we might have bricked some phones at some point, but this was not the dangerous part was not really the searching for the exploit, searching for an attack, searching for a problem there. But usually when we required to use a specific kernel version and then had to, for instance, downgrade a phone, and then the downgrade was not successful to an older firmware, and then the phone was bricked because the downgrade was not successful. So the problems usually don't occur while searching for attacks or trying out attacks, but while getting the setup right. How much speed up are the predictions? How much speed would we lose without them? So it's not entirely clear because you can't just disable that. In some parts you can disable that, and the estimates range between factor 8 and 80, something like that. It's not clear how much precisely, but at least 8 times slower is a good guess. Breaks song slabs. Okay. Silicon fix. If you, I'm not sure what the exact question is. So if you would just rephrase that, it would help me to answer the question. So you're in the red team. Oh no, I'm in academia. I'm not in a company, so I wouldn't say I'm in the red team. How can you determine the bit to flip? So with rowhammer, you first flip random bits, and as soon as you have found a bit to a memory location where you can flip a specific bit, specific offset, you would reuse this offset and place the data structure of interest exactly there, and you would get the same bit flip again if you rowhammer again the same location. So you can first search for memory locations where, when hammered, a bit flips at precisely the offset that you need, for instance, for the pseudo binary for the password check, and then later on place the pseudo binary at exactly that physical memory location, and then you flip the bit. What is a silicon fix? A silicon fix, in contrast to a software patch, a silicon fix is a hardware patch. So that means not just an update, a BIOS update, firmware update, software update, but a patch that is implemented in the silicon, in the processor, in the silicon that the processor is made of. I did not quite understand the bit flip part. So are we changing the memory by changing the capacitors? Yes, we are reading from memory locations. I can show you a video of that. Let me show you a video where you wouldn't be able to see me while I do that, I guess. Just give me a second. I will show you a video, but I need to find it first, and then I also need to enable this in OBS. So let's find the video. It's here. Here, I got it, and now I need to switch to the just give me one more second. I need to copy in the paths so that everything works. I probably can edit here. Let's add this here. Difficult. Showing a video is not so easy. Okay. It's here, and then this folder, and It's an older video already that I've created for a conference at some point. Okay. Let's see whether this works. Yes, this works. Let me make this a bit larger. Unfortunately, this looks a bit weird. Yeah, I would like to change the form factor of this one. It doesn't look right. Transform. How do I stretch this? This works. Okay, now you can see it. So in this example, we first use the DRAM side channel, and this DRAM side channel is this timing measurement that we've spoken about. And we will measure, basically search for addresses that are conflicting with each other. You can see the timing histogram. It's plotted here in ASCII. And we are searching for all the different address sets. That means all the banks. We've said there are 16 banks on DDR4 and 8 banks on DDR3. And in this case, we would find these different sets. And we found them now, and they are determined by address bits. You can see that here 6, 14, 18, 15, 19, and these addresses are usually these address bits are XORed together, and they determine whether it goes into one bucket or into the other. So we have 1, 2, 3, 4, 5, 6 functions here. Is that correct? 5 functions here. 6 is 6 is wrong. We don't need 6, but the others, 5 functions is good. And so we would have 32 different buckets because we have 2 channels, 2 ranks, and 8 banks per rank. That makes 32 sets. Now we run row hammer with this function. So we hammer 2 memory locations, and now we will allocate a lot of memory and check where the bit flips are. So we hammer 2 memory locations. And now this is every number represents the hammering of 2 memory locations. And now we try this again, and we see a lot of bit flips. You can see that here, a lot of bit flips. Really a lot of bit flips. This is too many bit flips. So maybe let's go for a second video there. Do we have a second video? Yeah, maybe I don't have a second good video now. Yeah, don't have any second good video now. So maybe that answered part of the question. Let's go back to the question and check whether there's any more I can say to that. Are we changing the memory by changing the capacitors? So the capacitors will stay where they are. We are not doing anything physically here, but we are changing the charge of the capacitors. We are discharging capacitors that we cannot access because these capacitors represent the memory content of other processes or the kernel. When using ECC or different memory modules, might it be that not the same bits flip? Yes, but with the same module, you would see always the same bit flips. Also on an ECC module, if you see a bit flip, it is very, very, very likely that this bit flip would occur again, and that you can reliably trigger this to induce a fault, to change a data value in another security context. What about the security issues in the new Apple M1 CPU? I think at this point no one has studied the new Apple M1 CPU yet. Is it too early for that answer? The Apple M1 CPU is certainly very interesting, and I think many security researchers will look at that now. So that's about as much as I can say here. Would it help if only static predictions for branches were allowed, included by the compiler during compilation? Let's assume I always predict, for instance, in this example that we had before, we had two branches. The left one was leaking and the right one was not leaking. But also the left one was the more expensive one and also the one that would be executed in all the legal cases. Every time it is in bounds, which is the proper use of this function, we would speculate in bounds. So if you would statically say, oh, always speculate to the left, then things would actually get worse because you would always leak. You wouldn't even have to mistrain. So with static predictions, you don't change the nature of Spectre. You just make the mistraining either easier or impossible, but it would not prevent the misspeculation. The misspeculation would still happen, and that means some form of data leakage would still happen. How do you get a specific page to the vulnerable PPN? That's a tricky question. Let's assume I want to flip a bit in a page table, and in the page table I want to change the user space accessible bit. I know which bit offset this has in a 4 kilobyte pages in 4 kilobyte page. Actually, on a 4 kilobyte page, if you think about a page table, you have 512 user space accessible bits, and they are at 512 offsets of this 4 kilobyte page. Let's assume you search for bit flips and you find a bit flip which is on a 4 kilobyte page exactly at the right offset. Then in the next step you would release this memory. You would release all the memory except for the 2 pages that you needed for hammering. In the next step you would mmap a file as shared memory over and over again, always the same file. And this would give you a new virtual address every time. So this fills your virtual address space with always the same mapping of the same file. By doing that, you have to create more page table entries and more page tables, so you would fill the entire memory with page tables. And that means if you fill the entire memory with page tables, that also the vulnerable PPN with a very high probability will contain a page table. And then you trigger the bit flip again. And now you have changed the permissions on this page. And you can just iterate over the pages now and check whether or not an exception occurs. You can catch the exception, for instance, with a signal handler to avoid the program, to prevent the program from crashing. This is also what we do in the meltdown attack. We use a signal handler to prevent the seg fault from occurring. And then you would see where a page is accessible without a seg fault, and then you can just read the data from this page. The same would also work for changing read-only to writable, for changing the physical page number of a page. You can change the physical page number to something else, and then it would point to another page. So a lot of possibilities here. Can you also answer the questions in the YouTube chat? So let me see what questions are there. So we already answered the ECC memory questions. Can we never know what bits are flipped? So I would not get a lot of tries to get where I want, right? But you would know which bits you flip because you would first try this with your own memory that you have fully under your control, and with your full control, you are able to determine which bits exactly flipped. This is something that you cannot prevent because the user will still be able to allocate as much memory as it likes, basically. Simple CPUs are not affected by side channels. Oh, they are definitely affected by side channels. Cache side channels just work on RISC-V as well. Caches basically every small processor nowadays has a cache. They are affected by side channels just the same. They very often have different security models. So for instance, if you take a very small RISC-V core, or if you take for instance, a very small ARM core, the ones that you would find in chip cards, for instance, they might not have a cache, but they also don't have any security domains. If they don't have security domains, then of course it doesn't matter. But virtually any chip that has a security domain also has a cache, and that means side channels exist on all the processors that are relevant. Also, all these processors use DRAM. If you use DRAM, you already have a side channel, the row buffer side channel. Of course, you can avoid using DRAM, but similar side channels also exist for SRAM, because SRAM also works in a similar way. You can distinguish timing differences between is it in SRAM, or do I have to fetch it from a slower storage like an SD card? You can observe a timing difference. Side channels are so inherent to everything, to not just computers, also our real life. You have side channels everywhere. For instance, if you sit down on a chair and you notice that the temperature is higher than you would have expected, you can be fairly certain that someone was sitting there before and it's not the chair that is heated. So this is a side channel. You haven't seen that someone was sitting on the chair, but you have the metadata that someone must have been seated on this chair, because otherwise it would not be warm. If you put, let's say, if you put several beers into the fridge, and then you open the fridge at some point, and instead of beers there are now other things in the fridge, then you can infer that someone must have opened the fridge. You haven't seen that someone has opened the fridge, but you can infer that someone must have opened the fridge. So side channels are very inherent to our everyday life. They are very inherent to computers. You will not get rid of side channels. RISC-V cores, also if you talk about vulnerabilities that are a bit more sophisticated, like Spectre and Meltdown. Spectre has been demonstrated on RISC-V cores already. So these, as soon as you add these optimizations, these attacks work. So these are two sides of the same medal. You don't get the optimization without getting the side channel. You don't get the optimization in case of Spectre without getting the leakage from speculative execution. How would you design RAM so that it is not vulnerable? I'm not a RAM designer. So if you want to ask like that, I'm more teaming up with the red team because I'm better at figuring out what goes wrong than at figuring out how to design something in a secure way. I've done that in some cases. We have published papers on how to make things secure, but in many cases we focus on what goes wrong and why does it go wrong. So, but for DRAM, you would have to study probably for many years until you would actually be able to design secure DRAM. So I'm not doing that. Can we see the source somewhere for Rowhammer? For Rowhammer, the code is on GitHub. You can just search for GitHub EAK Rowhammer, and you will find our GitHub repository where you can see the source code, and you can run it on your own system and see bits flipping on your own system if you like. Okay. Would Rowhammer-like attacks be even more prevalent on SoC chips since the components are even closer? That's not necessarily the problem here. So on SoC chips, I would expect that the nanometer scale on which things are processed is larger actually than on these very modern processors. If you think about something like a recent DRAM module where they have structure sizes around, is it 7 nanometers, something like that. 7 nanometers, that's very small, but also more expensive than choosing a larger processing technique. So for the high performance computers, you would have the lowest proximity, the highest proximity between different cells. So on SoC chips, I would expect a lower proximity. So is a larger cache in a processor, a larger cache in a processor is worse for security? I'm not sure whether the size actually is a significant influence factor here. Actually, if you have a larger processor cache, things like flush and reload might become a bit more powerful, but they are already very powerful. So for flush and reload, it would be an advantage because things might stay in the cache longer. For things like prime and probe, I would argue that it's actually a disadvantage to have a larger cache because you have to fill some fraction of the cache to be able to mount an attack. So it makes the attack slower and probably also more noisy. So you would need more measurements, and at the same time, it would take longer. So it would take longer based on two influence factors. So I clocked down my CPU. I don't know why you would clock down your CPU. There's no advantage in that I would be aware of. Disable hyperthreading and I'm safe. Disabling hyperthreading is something that many people recommend if you want to be very secure. But the question is always, what is your threat model? And for many people, probably this is not the most relevant threat. For most people, the more relevant threat will be an email that they get where they are asked to send money to someone, and they do send the money to this person. So this is probably the more prevalent threat that everyone is, or many people are susceptible to. So I don't think these attacks. I don't think that any participant in this course would be a prime target for these attacks. Of course, if you are either if you are working for a secret agency, or if you are working with really sensitive data that a secret agency wants to get, or if you are in a context where you cannot freely express your opinion, so where you might have an oppressive regime, then the political opponent, people from that are among the political opponent might be attacked with more sophisticated attacks, but for a usual person, for the average person, these attacks would be way too expensive to use. Does quantum computing change that? No, quantum computing won't change this, and I'm also skeptical that quantum computing will will introduce significant changes within the near future. On the long run, it might make some things more efficient, some things less secure because it can do new things. But for many of the techniques that we use today, quantum computing will have no influence at all because they are not doing anything that quantum computers would be better or worse at executing. It's just an orthogonal technique. It's just a different way of writing algorithms, of approaching problems. Thank you. With that last question, I think that was a really good question for the end, a really good comment for the end. So thank you. At this, I will already close the Q&A, and thank you for your attention, and I will close the presentation, and thank you for being here.